Okay, so today I'll be focusing on the Langevin equation and the Fokker-Planck equation. So a tiny bit of background. So both of these equations are based off of a process of stochastics, thank you, where Brownian motion is the most simplest version. So it's pretty much a heavy particle of mass and velocity that is moving in a liquid consisting of light particles. This is known as the Brownian particle. And then this particle is subject to random collisions with the molecules of the liquid itself. And then this gives rise to an average frictional force on the massive particle known as the, what was the word again? Stochastic force, known as Ft, that fluctuates around an average value. This is very important in the first equation of the Langevin equation, because this information is actually used to make the equation itself. So under that stochastic force conditions, the Newtonian equation of motion becomes the Langevin equation, which is given here, where this is that stochastic force that I talked about on the last slide, M is mass, V is velocity, and then the fancy C in this case is a coefficient describing the friction between the particle and the bath. So
first term is frictional force.
I'm sorry?
Your first term is frictional force or different force? What kind of force is the first term?
You have stochastic force F, but your first term in this after equation equal sign, does it include
this term?
Does it include friction?
Is this frictional force or viscous force or what kind of force?
In other words, your energy is conserved or not? Because if you have friction, the energy is not preserved in the system. You have dissipation to the surroundings. So that's why it's important. Is your equation, Newton's equation, preserve the energy? So means frictionless forces or not preserved?
So dissipation does come into effect later, so that makes me believe that.
Yes, what would be the alternatives? What other characteristics could be assigned to a random force?
Some frictional force.
But are there any other ways to describe the random force?
Yeah, you can have frictionless
random force, not friction.
Oh.
Can you have an example? Or your equation is only symmetric?
For the model, you can neglect the friction. In the reality, you of course have friction, but for the model, you can just neglect the friction. It's possible.
But Dinesh is asking about F, the random force.
I'm asking your first force, first term.
The first form is just mass times velocity.
Oh, maybe.
But I think he's talking about the first term on the right side of
yes,
the MC.
Okay.
Information about friction should be in the after the equal sign, right?
So this Greek letter Z is friction.
It's friction.
That's Z, not C.
C, like the hair-looking one. That's a capital version.
You can argue for another 4 hours.
Okay.
I thought it was the calligraph C. Okay.
Pronounce it
Analog of English C.
Okay.
Just to act like
What?
Your question, time derivative of velocity and acceleration. The what? Time derivative of velocity and acceleration. Yes, but that's not time derivative of velocity.
It does.
No, I mean the second one.
Because that's
Second one's just
As a what?
drag force.
The
Drag.
drag.
Yeah. Of like your particle moving through fluid and getting bugs from all different directions and stuff.
So it's mass times velocity.
What's it?
That term proportional to velocity is friction.
Yeah, basically.
Thank you for provoking intense discussion.
I guess the question was how to connect the first term after the equation to the force. So we have momentum mv, right? And then some strange letter which stays for friction.
Yeah.
And again, you probably can Google this in physics. So overall, it gives you the force.
Okay, so this is the very generalized version of this equation. So this is pretty much the beginning equation, but depending on how you swap things out in this equation will give you different end equations. So in that process of putting stuff in, switching it to try to get it relative to your specific case, you come with this correlation time, tau c, which denotes the time in which the fluctuations of ft remain correlated. So this is the amplitude of the randomness happening in ft. So tau c is in between these two. So this is where between this and this, those fluctuations remain correlated to each other. And that is used later in when you do all the math to figure out the end equation that you're looking for. And then with this equation, it is safe to assume a few things. So the random force is equally likely to push in one direction as it is in the other direction. So the average overall realizations of the force is 0. So that's where we can make this assumption. And then also the random force exhibits no time correlation, but has a coefficient g in this case, which is a measure of strength of the mean square deviation of the stochastic force. So, yeah, so I did not give an out equation just because there are so many, but you can correlate the Langevin equation to my next equation, which I will talk in a little bit more detail later. But for the Fokker-Planck equation, again, this top one is the more generalized one, just like the last one, depending on what you are particularly looking for, it changes at the end. So on this one, I will go over 2 different final variations of the Fokker-Planck equation. So as talked about in the other laser classes, we already know what C is, and then alpha and alpha star in this case is alpha is the annihilation operator and alpha dagger is the creation operator. And then this term right here is actually the P, I'm thinking on the word, the P representation, which is also known as the coherent state representation. So this is what that equals, where this is the average mean. And then D is...
Intervene. Yes. So no question, I just make a comment so that we develop slowly but surely. So the first line that Tori has introduced is an equation in partial derivatives, right? So instead of this dot, there are derivatives over alpha, first and second order, and derivative over time. So it is something that develops in time and some space. So it is distribution as function of alpha and alpha star. Tori correctly mentioned that alpha and alpha star relate to creation and annihilation operator, but to be more precise, it deals with amplitude of coherent state, with eigenstate of annihilation operator. And the amplitude of annihilation operator is equivalent to is proportional to the strength of electric field. So in some sense, the distribution that Tori is describing is how probable is to find that electric field has so large strength at a certain time. And then she's going from declared partial derivative equation to its solution. So there are two independent space variables, one time, and here the solution is oscillating Gaussian, oscillating two-dimensional Gaussian, like Patricia was doing her projects. Okay, sorry for the interruption.
No worries. I guess I forgot to mention that this is one of the solutions with a whole bunch of math. There's multiple pages of it, so with the limited amount of time we have, I didn't want to get into that. But the D is the dispersion of the Gaussian function about the mean value, like I said earlier, is this. Okay. So we have a function, well, we have an equation now, and this is the figure that goes with the equation. So this 3D part, as we can see, is that Gaussian distribution that we are used to, just in a 3D format. So at the beginning, at initial time, which is kind of hidden by this, but this is initial time of the P representation. The entire equation starts here, where D is at the initial value of 0. So currently there is no dispersion of the Gaussian function whatsoever. So if time were to stay stagnant, it would just go around this dark black circle. And then once we actually start getting into time, we get away from that excited state and start going back to the ground state. And during this, we have the dampening effect that occurs, causing it where the average value, so the dampening is pretty much here, will start oscillating slowly into a spiral until it gets to 0.
How should we interpret your axes, the imaginary alpha and the real alpha here?
So Stephen explained the imaginary and real, but this entire thing is in a pure coherent state of ket alpha. So I'm assuming that's where the imaginary alpha and real alpha come from. And this is the coherent state that the entirety is in. Does that answer your question?
Do you want to give her time to Tori, or you want to ask?
I'm fine with either.
So real and imaginary parts of alpha will be proportional to electric field amplitude and to derivative of it. And in this sense, this phase diagram is very similar to what one does in classical mechanics for position and momentum, also going in circles. But since it is damped, instead of going in circle, it goes by spirals, ends up in the center. You're satisfied? Tori, you're okay. Just continue.
Trying to think if there's anything else for this image.
So why does it peak up in the Z dimension just like toward the end? Of this, I would say by the end of this decade, like why is that peaking up much more in the Z dimension versus like earlier on?
Can you talk about this part?
The peak is moving entirely through space with respect to time.
Oh, so
the dot line is tracing the path.
Okay, so this is just showing it mid. This entire 3D part would start here and just slowly move around.
okay.
Sorry, so does the center of, based on my understanding, like what I'm understanding, so does the center of this means that that's the ground state?
The center. So when this gets to here,
Yes.
yes, that would mean that it's back in the ground state. Yeah, because when it's here, it's in the excited state, and then it slowly makes its
So
way.
like you get like the first ground state Gaussian function, like that. Looks like the ground state Gaussian. Is that why you keep that shape?
It's like, yes, sorry.
So at 0 temperature, it would relax to a ground state of the oscillator. But if the temperature is above 0, then it will increase the width. So for thermal state, it also centers at the equilibrium point, but the width is broader than for a Gaussian for the global stage.
Okay.
Does the angular momentum vary with time?
No angular momentum. If one wants to apply to classical or to any harmonic oscillator in terms of position and momentum, then it's linear momentum. Position and momentum, they make a circle in a phase space, not in a real space. In a real space, position oscillates like cosine and momentum oscillates like sine. And if you do parametric plot, it will be a circle. But there is no momentum, it's linear oscillator motion. Does that answer your question?
Okay, so like I mentioned earlier, that the Langevin equation can be used as well. So the P representation also helps with the correspondence between the density matrix and the Langevin equation through the equation of motion of the P representation. So this is the final result. So pretty much there was a whole bunch of math.
Intervene and do like a little, how to say, comment, editorial comment. So Tori is telling everything correctly, but additional comments so that we stay on the same plane or same page. In previous couple of slides, she was given an equation and solution, right? And equation and solution were corresponding to the limit only when one has the losses introduced to us by Helm. Then there is a version of the same equation in case if there are gains, if there is a pumping. In case with pumping of the mode of the oscillator of the resonator mode, equation would take the whole page just to write down. And therefore she's skipping the equation. Then Tori is introducing to us the solution of Fokker-Planck equation with both gains and losses. And there is one more comment. Before we had a nice picture with spiral, because it is quite predictable what system does if it is created in the excited state and then it slowly goes to ground. But if you have a pump and you wait long enough, it will very quickly arrive to the saturation regime, and then it will move there randomly and we will not remember what is the phase. So it will perform some steady state solution, which time component will be just regular oscillations with a given frequency. And Tori is skipping all these details and provides us only steady state solution for the Fokker-Planck equation in the limit of both pump and down. Okay, please continue.
Okay, so this is the end equation. Like I said earlier, where A, like we said before, is the linear gain coefficient, and B is the, there it is, B is the self-saturation coefficient, and then N is actually the normalization constant. So near the threshold, the steady state solution of the equation of motion, which is this, RA here is also a constant, right? But so that's the linear motion when you're near the threshold. And then the figure is the phase diffusion model of the laser line width, which is what this equation helps. Well, the line width helps with this equation. So it pretty much helps you find the solution for the equation when you actually go to solve it and put in all your values and stuff. So this is the electromagnetic field as a complex vector. And then with experiences of small changes in the phase due to the spontaneous emission events that are occurring, these changes are totally random, so there's no way to know exactly where it is. That's why all these dots, there's no pretty much rhyme or reason besides them going in the 2π sphere. But the phases gradually diffuse and becomes equally distributed over all of the 2π's, which is why you can kind of see that sphere-like thing, even though this is supposed to be totally randomized. There is an average of them all. And then it is assumed that the laser is operating sufficiently far enough above the threshold that the amplitude fluctuations can be ignored for this one, unlike with the other one where we had to apply the amplitude and what made it have that spiral.